finally gotten to the point where we are going to be able, at the end of our class period today, locate every single electron in an atom. So right now we've gotten down to, we can get to the street, and we know how many houses are on the street, so now we'll know which house to look at. To start doing that, a visual representation of where the electrons are is an orbital diagram. So that's kind of where we're going to begin. That's going to help us get to our goal, which is electron configurations. But there are two ways to get to electron configurations, and I'm going to show you both. So the diagram is more visual, and then the actual address of every single electron is in this form, an electron configuration. When you're trying to figure these out, there are three rules to follow to get them correct. The off-bound principle, the Pauli exclusion principle, and Hund's rule. So the off-bow principle gives you a rundown of how the electrons are going to fill the electron cloud. It gives you an order to go by. It says that you're going to go with the lowest energy orbital first and fill from there. So we can figure this order out if we know that they go lowest energy to highest. So think about your principal energy levels. are the lowest ones going to be the ones toward the nucleus or the ones toward the outside? The ones close to the nucleus. So what number is going to be closest to the nucleus? 1, right? So according to Aufbau, we're going to start with energy level 1 and fill that first, what's the only sub-level in there? S. So we're going to start with 1s. Are there any more sub-levels in 1? No. So we go ahead and bump up to energy level 2. First sub-level in there is S. What goes after that, would you say? P. 2P. Good. Are there any more in level 2? Nope. So we're going to bump up to 3. And our first one's going to be S. What's next? 3P. 3P. And what do you think would be next? 3P. You would think so, wouldn't you? It's one of those exceptions to the rule type situations, which sucks big time. But follows the pattern again, so it's not as bad as it could be. So that's what the scientists said. They're like, well, it should be 3D, but they actually do their measurements on these sublevels, and they come up with this chart that goes from lowest energy to highest. And so I know it's hard to see from back there, so I'm just going to point them out. This is the 1s down here, lowest energy, like we said. There's 2s, 2p, 3s, 3p, but that's not 3D. That's 4s. So what they actually figured out is that the 4s sublevel is lower energy than the 3D. Same with 4D. The 5s sublevel is lower energy than 4D. So when you're doing this order, you have to remember that. So instead of 3D, we're going to put 4s. That's what comes next. After 4s would be your 3D. What do you think would be after that? The 4p. Good. Okay. And what do you want to put now? We wanted to put 4D, but we know it actually has to be 5s. And then your 4D would come after that. Okay? So it's not quite what we think it would be, but you just kind of have to flip those a little bit. So there's an order, there's the order that we're going to use to fill up the sublevels. And that's as far as we need to go for now. I don't think any higher than that is necessary, especially today. So moving on to our second rule, Pauli exclusion principle, which half of this is old information. It says 2 electrons can occupy a single orbital. We already know that. That's old information. The only thing new that Pauli says is that if the 2 electrons are in the same orbital, they have to have 2 opposite spins. That's the new information for Pauli. If the electrons are in the same orbital, they have to have opposite spins. And this is much easier to demonstrate, so I'm going to demonstrate that rule when we get to an example here in a minute. Hund's rule is very wordy, so there's not much point of writing it down because it's not going to do you much good. So write what I say, not what you read. Okay? This is what Hund's rule says, so I'll let you read it for a moment. Then I'm going to summarize it. Yep, you read it and went, nope. what do you think? Okay. If there are equal energy orbitals, put one electron in each before adding a second. Do I need to repeat that? Okay, looks like we're good. So, I'm going to show you the goal that we're trying to get to. So this will show you how much progress that you're going to make in a few minutes. This is what an electron configuration looks like. Okay? And I did not show that to you to make you crap your pants. I showed that to you because you're going to see that even though this looks intimidating, it's really nothing. It's one of the easiest things you're going to do all day. Okay? Alright, let's try it. First example, we're going to start with an orbital diagram. We're going to start with simple examples and work our way up. The example that I'm going to use first is beryllium. And the first thing you need to know if you're going to make an orbital diagram is how many electrons are in beryllium. 4. You guys all see it up there? Beryllium has 4 electrons. So 4 electrons is all we need to place in the diagram. So, first step, we're using this order. So the first electron is going to go in this sublevel right here. So I just write it down. 1s. How many orbitals are in any s sublevel? Orbitals. 1. So we're going to put 1 line over the top of it like that. Then off to the side, we're going to say that line represents an orbital. And how many electrons can one orbital hold? 2. But I need to place 4. So that means I'm going to have to go up to my next step to get the rest of those in there. So we're going to write the 2s. And it's an s sublevel, so I just have the 1 orbital again, right? To place your electrons, only 2 can go in each orbital, of course, and then you have to use Pauli's rule. This example is going to use Pauli's rule. He says if there are 2 electrons in an orbital, they have to have opposite spins. So the way that you show that is you go, well, there's electron number 1. It's kind of like a half an arrow, and the upward shows the spin. And so the other electron that's going to go in there with him has to have the opposite spin. So you show it like that. So there's electron 1 and 2, and then there's 3 and 4. And from that, we can get our electron configuration. You go to the first sublevel where your electrons are located, which is in the 1s in this case, in every case actually, so that's always the order. How many electrons are in there? 2. So you put a 2 as a superscript. Go to the next place where your electrons are located, the 2s. How many are in there? 2. That's your electron configuration. So you look at the superscripts, and if they add up to your total electrons, you're probably right. So you can always double check your answer. So As simple as that. So beryllium's electron configuration would be 1s2, 2s2, not squared. Don't say squared. Squared is a math thing, not an electron configuration thing. Okay? Easy enough, right? Okay, let's go step up. Second example we're going to do is oxygen. How many electrons in oxygen? 8. That's step 1. 8 electrons that I need to place. So 1s always goes first. There we go. So it's going to be 2 electrons in there. So I need more. So I bump up to the 2s, which can hold 2 electrons. So I got to go up above that. So the next place I'm going to go is the 2p, right? How many orbitals are in any p sublevel? 3. So that means I don't need 1 line, I need 3 lines. So total electrons I could use right now would be 2, 4, 6, 8, 10. So that's going to cover oxygen, so we can stop. So now, use what we already did. So there's electron 1, 2, 3, 4. Okay, now I'm going to have you watch me place these last 5. No. 4. Count. You gotta count. Okay, I got it, I promise. Okay, so I'm gonna have you watch me place these last 4 because this is where Hund's rule comes in. We showed off bows with our order, we showed Pauli's with our opposite spins. Now we have to do Hund's because these are equal energy orbitals. They're all in the 2p. Make sense? Okay. They're equal energy orbitals, so it says you put 1 in each orbital before you start adding the second. So you're going to go 5, 6, 7, 8. One in each equal energy before you add the second. So there's your orbital diagram. So you guys tell me, what would my electron configuration be? 1s2, 2s2, 2p what? 4. And if I add up my superscripts, it gives me 8, so I'm right. It's not hard. Pretty easy, in fact, right? Okay, I'm going to take your stoic silence as, yeah, this is easy, let's move on. Okay, I'm going to give you a little bigger one to do, and this time I'm going to have you do it on your own, and then I'll check it. Or I'll do it up here and you can see how you did it, I guess. So you guys try this one. Do something a little bigger. So I'll give you a couple minutes to get your orbital diagram and electron configuration figured out. We'll do it up here and you can see how you did. Alrighty. Okay. Total electrons was 14. So it would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. I see that there was at least some success. So, what would your electron configuration be?
1s2,
Mm-hmm.
2s2, 2p6, 3s2, and 3p2.
Very good. So that's it. Easy stuff, right? Okay, we're cooking. We're going to do one more example, and it's going to be the biggest one. Okay? Go ahead and do that guy. And germanium has 32, correct? All right, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12,
13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay, which makes your electron configuration that. Okay, go pretty well? What happened?
I
The 3D?
I totally forgot about 3D.
3D? Okay. That's easily fixed. Okay? Alright. But like I said, there's more than one way to do this. So that's the first way. Now I'm going to show you the second way. So, Mara,
Yeah.
I want you to pick a number between 45 and 50.
45 and 54.
45 and 54. Pick a number.
Wait, what was the second one?
Between 45 and 54.
Dang it. 50.
50. Okay. So I'm going to do the electron configuration for 10. Are you ready?
That was a hard question.
Alright. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p2.
Ow. That was a spell.
Yep. Makes me look like a total genius, right? No. Totally, yes, I'm a nerd. I'm about to nerd out hardcore because this is exciting. Because this is where you finally get to see how cool the periodic table is. Because where did I look the whole time?
Periodic table.
Right there. So this is telling me what I need to know. It's just you have to know the secrets. Okay? So I'm going to do this one more time, slowly, and I'm going to point what I'm reading. Okay? So I want you to just observe, pick up any patterns that you can. Alright? Here we go. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p1, 2. Read it like a book, left to right.
No.
We're going to do it several times. Okay. What I wanted you to pick up on, where was I every time I said an S? It's over here, right? How many electrons can go in an S sublevel? 2, right? This section is too wide. Okay, where was I every time I said a P?
Over here.
It was over here. How many electrons go in a P sublevel? 6. This is 1, 2, 3, 4, 5, 6 wide. How many electrons go in a D sublevel? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ta-da. Just have to know how to read it. So, I'm going to give you the key to the kingdom. It's your choice. You can go through that, or you can read it. I think by the second day, you'll be reading it. Actually, by today, you'll be reading it. Okay, so something that would be extremely helpful for you is to just draw a little sketch of the shape of the periodic table. Don't have to have the squares in it or anything. Just draw the shape, the outline of the periodic table. this is part of the S as well. And that section of the periodic table is actually referred to as the S block. So that'll make things much easier even when you're looking for an element. If you ask me where can I find it and I tell you it's in the D block, you'll be like, it's right there. Look, a little crazy. A little crazy. I'll fix it. So there's your D block, right there. There's the P block, which only leaves this, which is the F block. So that tells you what to read when you're in that section. And do you remember me telling you how many actual rings should go on Bohr's model? Like I went out to 4, but you remember me telling you the actual number? 7. Goes to 7. So I know what principal energy level to say in front of S because I can read it right there. 1s, 2s, 3s, 4s. The only one that's off is the D block because it puts it in the 4th period, but this is actually 3D, right? Because 3D comes after 4s. So when you read it like this, you can't mess up putting the D block where it's supposed to go. Okay? Alright, I'm going to do another one slowly, and then you're going to do one. Okay, I'm going to do argon right here to start with. I'm going to do it slowly, and I'm going to point. Okay. So 1s2, 2s2, 2p6, 3s2, 3p6. Are you ready? Now all you guys are going to say it. The more that you do it, the better you get. And you're doing it all together, so I'm not going to be able to hear just one person. Okay? I'll point it out and you say it. Here we go. Okay, go wild. Be crazy.
1s2, 2s2, 2p6, 3s2, 3p6.
3p6. Easy, right? Okay, we're going to do one that's a little bit more.
Right on.
And just lock in. I want you to lock in because we got to go past the D block on this one. We're going to do bromine. Okay? JD, if you trick me, you die. Okay? Alright, here we go.
1s2, 2s2, 2p6, 3.
Okay, wait a minute. We're going to start back here.
3s2, 3p6, 4s2, 3d7, 4p6,
5. Just remember where you're
Where'd the
stopping.
5 come from?
1, 2, 3, 4, 5. We were doing bromine.
Oh, this sucks.
Okay? Easy. That's all there is to it. Okay. So since we're talking about electrons though, there's something very important that we have to cover while we're talking about them. 2 things actually, because they're used all the time and for the rest of the year. Actually, the rest of the class, not just year. So we finally get to talk about valence electrons. And you are going to hear that term until you are out of this class. We use valence electrons all the time. They are the ones in the outermost energy level, the highest principal energy level that still contains electrons. so now I'm going to show you how to figure out how many there are of these valence electrons. We're going to use germanium since we already have this example. And we said that they are the electrons in the outermost energy level. So look at germanium. What's the highest principal energy level that still has electrons? 4. You guys all agree with that? Okay, so we're looking at energy level 4. How many electrons are in there? I heard 2 and I heard 4. If I look at this configuration, energy level 4 shows up there, but it also shows up there. You have to total the 2. So there are 4.
Congratulations.
4 valence electrons in germanium. I would write that down. Okay? Easy to determine once you know how. Now flip back to silicon. How many does silicon have? I heard 4. Is everybody in agreement? That's correct. Silicon has 4 valence electrons, so write that down beside silicon. Three is your highest principal energy level. You had 2 in the S sublevel and 2 in the P. Total of 4. Okay, go to oxygen. How many valence electrons there? 6 is correct. 2 in the 2S, 4 in the 2P. Total of 6. Okay? Beryllium, last but not least. 2 valence electrons for beryllium. There's 2 in the 2s. So now I'm going to show you how the periodic table gets even cooler. It's possible. It's possible. Okay, we just said beryllium has 2 valence electrons, right? Here's beryllium. Look at that number. We said oxygen has 6 valence electrons. There's oxygen. Look what that says.
16.
We said germanium has 4. Look at that number. We said silicon has 4. Look at that number. So how many would argon have? 8.
I said.
Glad you clarified.
Yeah.
Okay, what about nitrogen?
5. Oh, I get it.
That's how cool the periodic table is. Best arranged table ever. Ever. Okay.
Why do I have the feeling you just have posters of that in your house?
I really did. I really did. I have a periodic table literally, like, there's like more than one. Anyway. Electron dot structures use valence electrons, so we're going to go ahead and talk about them as well. They could also be known as Lewis dot structures, so don't let that confuse you. And they are used a lot also, because valence electrons are used a lot. So the description is there. You have the elements symbol, and then you use dots to show the valence electrons. So I'm going to show you what one actually looks like here in a minute. Drawing. So Mara, this is right up your alley. There gets to be more drawing too. So
Oh my gosh, really?
yeah. This is just baby drawings. Baby drawings. I'm gonna do one for germanium, that's our main example. All you do is write the symbol for germanium, and then you just imagine a cube around that symbol. You put your dots on each side of that cube, and it has a similar rule to kind of Huns, where you do one on each side before you double up. Okay? So the one for germanium, since it has 4 valence electrons, would look like that. I'm going to show you the one for oxygen too, because it has more than 4. Oxygen has 6 valence electrons, we just talked about. So oxygen is going to look like that. See how I did that? One on each side, and then I doubled up.
Are you supposed to start in a certain spot?
No, doesn't matter. As long as you do the one on each side before you double up. This is correct. This is not. Don't do it. Put your dots on the side of the cube. Don't extend them out. People do that every year, and every year it's like nails on a chalkboard for me. Don't do it. Okay. One last challenge. As I said, by the end of the day today, you're going to be able to locate every single electron, right? So, using your example of germanium, because apparently I just like germanium today, locate germanium's 15th electron in your orbital diagram and circle it. What?
Does it record sound?
Yes.
Jacob sucks!
Okay. In what sublevel is the 15th electron? Okay, so it's here. Okay? Which orbital? 1, 2, or 3?
Three.
Some people said 2, some people said 3. Remember how you fill those.
Yeah.
Okay, so there's 12 electrons, right? Then I would go 13, 14, 15. That's him right there. So you could tell me that germanium's 15th electron is in the 3p sublevel in the 3rd orbital. That's how good we are today. And that's finally it for today.